understand all my inductors becomes capacitors. It will happen. Because if you do not understand the self-resonance frequency, what is the biggest problem here? Look at here. When an inductor having a capacitor, I am giving a simple case. Suppose this is an inductor. In your mind it is an inductor. But parasitic, there is a capacitance. Yes or no? Look at that. So now think about, I am looking at the impedance from this side. Now if you plot the impedance versus the frequency, what will happen? At zero frequency or near zero, it will behave as an inductor. So your impedance will go up. Then what will happen? If you go on increasing the frequency, it will go up and then swing to a very high level. This is known as the resonance frequency. After the resonance frequency, what will happen? It will behave as capacitance. So think of it, this is the frequency which is called the F self-resonance frequency. So if you are designing something where the self-resonance frequency, because of this LC network, you are not aware of this capacitance. So your impedance, whatever you are thinking of the inductive one, will be basically a capacitor. So maybe your self-resonance frequency of that inductor was 25 gigahertz and you want to work on terahertz. So the inductor will behave just as a capacitor. So that kind of confusing state will come while you design. Negative value will come. And you have to be aware of that parasitic effects. Okay?
How do you resolve this issue of
Yeah. In 65 gigahertz, first of all, the cutoff frequency of your transistors should be as high as possible. And then I go to the silicon process probably to be better for you, but just I will tell you that there is a special substrate. A normally high resistivity substrate is used to improve the cutoff frequency of the transistors. So you should have at least the cutoff frequency of transistors 10 times higher than the operating frequency of that. Second, all the components which you are trying to incorporate in your design, its self-resonant frequency should be as high as possible compared to the operating frequency. Then you cannot design. Okay? So those things are pretty important. You have to find out what is the, in case of transistor, what I said, the cutoff frequency. Cutoff frequency means the frequency of unity gain band. And the self-resonant frequency, just as explained. So those frequencies are the limiting factors. So you should make your operating frequency 4 times or 5 times, not even 10 times less than that. Suppose 2.4 gigahertz, then your cutoff frequency should be around 24 gigahertz. So you need a special transistors called RF transistors, where the substrate resistance is very low. So this picture is clear to you. So you need from the null parameter to the distributed parameters, and where you actually want this. Secondly, how it differs from the analog design to RF design. In RF design, there are few things that will come line by line, but let's come to the analog design, where the frequency is less than 100 kHz. Suppose I design an amplifier. Then in an amplifier, you must be talking about the gain. So the small signal AC analysis is good enough. You know that GM into RO. There is a gain, intrinsic gain of an amplifier. What is G? There is a transconductance. What is R? That is the output impedance. That is small signal analysis. So intrinsic gain divided by the attenuation is give you the gain of the amplifier. If there is a source degeneration and so on. So small signal AC analysis is good enough. Next important part is the linearity. Now what is that linearity? A linearity means that suppose I am feeding one signal, say 2.4 gigahertz. I would like to get 2.4 gigahertz at output. But How will you ensure? As long as the device behavior is linear. But all you know that any semiconductor is nonlinear in nature. IV characteristic itself is a exponential characteristics. And if it is exponential characteristics, I am giving an input periodic signal. You look at here, definitely it will give the nonlinear output. And nonlinear output introduces what? Harmonics. So 2.4 I will get 4.8. All those second, third, fourth, fifth harmonics. And those harmonics are nothing but introduce the distortion in your output signals. Now, while you talk about the linearity, then the most important part is how this exponential relationship will be linearized. What do you do actually? You introduce some kind of a biasing voltage. What do you mean by biasing voltage? It's called quotient bias. So you actually bias it, and then your input signal is very, very small around that biasing point. So within that, what is that? Suppose I am giving 1.2 volt quotient voltage, and I am varying the voltage, the input signal in microvolt. Think of it, within that quotient point, the variation is few microvolt, 100 microvolt. Then that is called piecewise linearization. So I do not consider any kind of nonlinearity within the exponential zone, a small part. Mathematically, what is that? Suppose that e to the power x is 1 plus 1 by x plus 1 by x, all these parts, x square factorial 2, x cube factorial 3. So I am introducing that linearity means I am actually negating all those second order and third order. So physically you have understood what is the linearity, and also mathematically you have understood what do you mean by linearity. But can you tell me why the device is exponential in nature? Simple questions. Why suddenly it becomes exponential in nature? Do you know the answers? Very simple. Electron energy distribution is Maxwellian in characteristics. So that's why all your IV characteristics are linear in nature. Is it clear? Only in the first order approximation you are basically linearizing that form, which assumes that your input signal to the gate of the transistor is very, very small compared to the bias. If you have any confusion, so this is linearity. So linearity, if it goes to the nonlinear region, that will introduce harmonics. But if it introduces the harmonics, what will happen? Suppose there is one signal that is one spike, but if you have more number of spikes, I am talking about the spectrum, this is the amplitude. So this is called Scott. But conservation of energy tells us what? Energy is fixed. Now, because of the nonlinearity of the systems, energy is now distributed along all the spectral components. What will happen? You require your fundamental components at the cost of your fundamental components. What does it mean? That the gain of the system will be lowered. So, if you look at an amplifier, linearity and nonlinearity, what will happen? This is my input and this is my output. So initially when it's a linear region, I need some kind of a linear gain, right? After that, what will happen? It will be lowered or it will be going up. Conservation of energy tells us amplitude will lower down because the energy will now distributed across other harmonic components. So in spite of going into the linear path, it will now drop. That is the nonlinear. This is the linear region. After that, the nonlinearity part will come. So that nonlinearity part means here harmonics are created and energy gets distributed about other harmonics. And we will define that if at what is the input level for which there will be a compression of the expected output when it is a linear, that V in is known as 1 dB compression. So that is the linearity of the systems. What is the next point? Is the stability. A very important features in stability. everybody says that when you first time started designing an amplifier, you will end up with an oscillator. Or vice versa, when you try to design an oscillators, you will end up with an amplifier. Why this kind of oscillations you don't want? Because suppose you are designing an amplifier, going to a simple 4-stage. So this is my input and I am getting the output. Okay. Now what is an oscillation? Oscillation means when a fraction of the output that is fed back to the input and added constructively, not destructively. Then at certain conditions called Barkhausen criteria, the system itself starts oscillating without requirement of external signals. I made a story out of that. Let's go to some kind of a lighter one. Say one student used to work in an engineering college, okay? And he used to get 2 rupees from every day from his father. And within this 2 rupees, he buy train ticket coming from Barashat and going to Jagatpur University. So whatever money is left, he used to use that money for buying his tiffin, means the after classes and everything. This way, father is giving money to him and he goes to the college and comes back. Then one day you find that in the train compartment, somebody is playing card games with money. And he is an engineer, must be more intelligent. He said, okay, it's a very good way. Let me try with my luck. So he's invested that 2 rupees, whatever money minus the ticket price. Then he won the bet. So he is getting money. In that way, finally, what happened? That his father is noticing his son is not asking for any money. 2 rupees, even 50 paisa is good enough, because he is able to multiply that money. And one fine morning, his son is saying last 2-3 days, not even bothering about fathers to ask him money. That means he is self-sustained. An oscillator is like that. Then somebody say jokingly that even the 2 rupees, father didn't give the money, he actually got it. The noise. So that's the way how the oscillation builds up. So the noise that actually responsible for noise, even for fraction from some balance or lose money, he gave that money and finally builds up that through gambling game and finally get unsustainable way of living, going to the college and having food and so on. But an oscillator, Barkhausen criteria tells that you don't need any energy like that, but that is basically ideal case. If you exactly satisfy the Barkhausen criteria, then you know that oscillation built up will be few nanoseconds. After that, the oscillation will stop. You need some additional energy to feed. So your A beta is not equal to 1, a little bit high, and then A beta is what? You remember the beta factor, right? So that little bit high you have to give, and then you have to reduce it like that. So that's the story, that how the oscillations will start. From stable oscillation comes over here. And then stability will come because you look at the output, this is the capacitance. So the output might, there will be fraction of the output from here will feed back to the input, and there will be an oscillations like that. So what is the culprit for oscillation? It's C, this is the drain, this is the source, this is the gain. So C, D, G. So a fraction of the output that will come where this capacitance and this input. So you have to find, so you may not be knowing that parasitic capacitance. But that is a finite capacitance which actually tells you that some kind of an oscillations might be done. Stability, no oscillation, or oscillation with fixed amplitude. In this case, it is going to the unstable state because my amplifier would have a fractional output come back to the input, and that will make the oscillation. Right? It may die down, but again it builds. So this is called the stability. So it is knowingly or unknowingly you have through the parasitic part. Knowingly means you remember that you have a resistance or inductance at the source. You know that there is a negative feedback that first year classes. So that feedback will come to your input. So there will be a known path of feedback. So those will create the instability into the systems. So S is the stability parameters that should be greater than 1. An amplifier, when you talk about linearity, like 1 dB compression, gain like dB, there must be a stability calculations. It should be as high as possible, right? And that will not come freely. So you have to compromise with something. Then in the noise, which requires a lot of discussions. So I will stop for 5 minutes, right? 5 minutes is okay? Then I will, because this lectures is getting videoed, so 1 hour is the maximum capacity of the cassettes, right? So you change the cassette now? So next one is the noise. Now tell me that if you have a signal, okay, what is the determining limit that below that signal strength you won't be able to detect the signals? Who tells you? Is the noise? The signal, if there is a signal here, suppose this is the noise floor. If the signal is below that, you cannot detect. But if you have a signal here, you can detect the signal. So the noise is that. We will go into the physical definition of noise later on. But I would say that you have to define for any RF system what is the noise flow. If you don't understand the noise flow, then you won't be able to detect what is the minimum signal. When I say that minus 112 dBm, so minus 120 dBm, if it's the noise flow, then I'd be able to detect that. Because minus 112 dBm is above. It's a negative value. Minus 87 dBm is higher than minus 120. So, for defining any receiver, the two things are important. One is the minimum signal strength that you can detect, that is defined by its noise flow, and what is the maximum signal it can faithfully transmit or receive, that is called the linearity. If the signal strength is above that, then what will happen? The nonlinearity will come, harmonics will be created, then distortion will come. So signal is bound by two boundaries. One is the lowest level by the noise, and the highest level by the linearity. In between these two, this is known as the dynamic range of a signal. For any protocol, RF system design, this is defined. The protocol tells what is the minimum signal you have to detect and what is the maximum signal you can handle. So that is the dynamic range. Now, if you look at the RF pull-up, where the frequency is more than 100 megahertz, then still this AC equivalent circuit is analyzed. Now you have understood. But when you will be designing the passive components or antenna, you will go for the 3D or 2.5D simulators. But before the linearity and stability and noise, there is another very important term coming, is the matching. S parameter, S11 or S22. Now you understand why this matching is so important. Because I have to ensure that the source energy gets maximally transferred to the load, or from the output side the maximum energy gets transferred to the load. So matching network is very important. Now the matching network also serves another task in RF. Can you tell me what is that task apart from the matching? It also acts as the frequency tuning circuits, because your so many frequencies are coming. Wireless communication, you have so many frequencies, even in particular band, so many channels. But you can select only your channel by this matching network, which is also acting as a tuning network. What is that? The resonant frequency of that matching network should be equal to your desired frequency range. Clear? So it has got dual role. A matching network acts as a tuning circuit as well as the matching of impedance transformations. So noise I have already explained. Stability, linearity, sensitivity. Now sensitivity is defined. What is the minimum signal strength you will be able to detect? That is depending upon the channel behavior. That is wireless channel or fiber cables. Whatever the channel characteristics, that will actually tell you. Plus the system noise, receiver, transmitter, those system noise, the signal properties, that will finally give you something in terms of bandwidth, signal to noise ratio, input preferred noise. All this come and they will finally give you an expression what the minimum signal will be able to produce. We will come into mathematics part later. And I will also mention about the dynamic range, which is the maximum signal you can handle minus the minimum signal you can handle. That is defined by the sensitivity, which is nothing but the noise. The signal should be above the noise. Come to the next. Somebody talked about how it differs from MMIC, miniaturized microwave integrated circuit, and RFIC. What is the difference of that, and why RFIC is becoming so important nowadays? If you look at the development cost, MMIC is based on, I gave a term, discrete. Means you have low noise amplifier, you have mixer, you have power amplifier, frequency synthesizers, and so on. Both are in the discrete level, but those are packaged in a high resistivity PCB, integrated, and then it is packaged in such a way that it looks like a single chip. But it is not a single chip solution, it's a multi-chip solution integrated in a package. Sometimes LTCC packaging or those kind of packaging are used. But the cost is lower, development cost. But if you look at the bill of material, then the cost is also low. But their scalability, that means from 1 gigahertz to terahertz, that kind of scalability is not there. And secondly, it takes more volume, more area. And it is difficult to implement for transistor, because transistors, you cannot have the matching transistors. Suppose one LNA, I need LNAs to be matched. So matching transistors is very difficult to get. Even for a single chip, 2 transistors, they have a GM difference of plus minus 5%. Now think of a discrete transistors, MO1, another transistor MO2. What kind of mismatch would have been? So that mismatch, so on. But if you look at the RFIC, the cost is very high, the development cost. But once this developed, then the fabrication is thus millions. So cost will be lower, right? And the scalability is much higher. Then it is lightest, low power, and so on. So these are the advantages. So that's why the RFIC is becoming so popular nowadays, utilizing the advantage of silicon, modern silicon technology, where MMIC is now gradually going to a very, very specialized applications, where the frequency range is very high, where the area is not so important. But here, if you have really a small area, 1 millimeter to 1 millimeter, then this kind of MMIC would not be. And nowadays the MMIC is primarily non-silicon, okay, like gallium arsenide, gallium nitride, those high electromobility transistors, those are used. But even now the tendency is to integrate those non-silicon, that is group 3,5 compound based semiconductor transistors, integrated in a single chip. Okay. So that is the advantage. So what is the topic that we are just discussing? This is a complete transceiver on the chip. Now think of it, that all the inductors, the capacitors, and even you cannot find where actually those active components. Because if you normally see any design, which will be in the next half, you will see the design and the layout. You will find that not even 10% of the total area is covered by the active area, that is the transistors. 90% area is covered by inductor, capacitors, connectors, and so on. So that is the compactness of the form factor of the design. Is now the challenge is only towards the passive. Because active regions, you know that the device is already in a nanometer cap. So not large area will be used. The next one, thermal cutoff. Okay. So what I try to say that, suppose we talked about any RF circuits, there is gain, right? One important thing. Second say linearity. Third one say power consumption. Third one is say stability. Fourth one is say, so let's consider the noise figure and so on. Now, if you want to design any RF block, any functional modules, suppose you want to have high gain, and at that time you want to lower your noise figure. How much? What is the probability of getting success? That you try to get the minimum noise figure, lowest noise figure, and the maximum gain. That is your objective. But you know that any RF design, all these parameters are interlinked. None of the parameters in RF design are independent. If you want to change any one of them, then other will be affected. So you can never get any design where you can say that I have done maximum gain and minimum of this, but you can say always an optimum design. So don't go for suboptimal, but an optimal design. So in RF there is no such thing like maxima and the minimum, but there is only thing is optimal design. I can give you a very simple examples why you require an optimal design. Again, I going back to a simple thing. Suppose this is a source and there is a resistance R. It is the source resistance and that is the load resistance. The condition for maximum power transfer tells us that R is equal to L. So that is the also the condition for highest gain of an amplifier, because my input signal that is being multiplied, amplified. So if the input signal itself gets reduced, I will not gain the high gain. Therefore, I need my source impedance to be matched with my load, so the maximum power gets transferred to my load. Now, if you look at the condition for noise figure, the condition is entirely different. Where you will find, I will prove that mathematically, that for noise figure to reduce it, what is the noise factor you can have? Maximum 1. Okay. In that case, you need RL to be infinite. Think of it. I want to reduce my noise factor to 1, that is a minimum noise figure, 0 dB. Whereas that condition tells me that load should be infinite. But in this case, for maximum power transformations, the RS is equal to RL. What I try to say that the noise factor is equal to 1 plus your RS by R. So condition for maximum power gain equal to RS equal to RL. You can prove that to minimize the noise figure, this is the condition. So your RL should be infinite, then it should be 1. Yes or no? So in that case, you will say two conditions never matches. Therefore, you cannot have claim that in a RF circuit you got a huge gain with the lowest noise figure. No, you can say it's an optimal performance. In that case, what you will say that I will try to see something like that, some kind of impedance matching like that. So I know this is the point where I will get, this is the R value, this is say noise factor or gain. So some optimal value, I will find R equal to some value, in which I will get the minimum noise figure and the maximum, or that point what is the maximum gain. So in that case, we can say this is called noise optimized design, power constraint noise optimized design, or gain constraint maximum lower noise design. So those are important design steps which will come later on. But you understand in principle what is the optimal design. Another point is important, which is pretty intricate, that this RF design involves not only a device engineer or a circuit designer. It's very complicated. It requires actually all these ideas. You have to know a little bit of micro theory, communication theory, statistics, because random signals, transceiver architecture, basic design, IC design, CAD2, various wireless standards, multiple access schemes, that is protocol and the modulation scheme, and the signal propagation and so on. So you have to make a very, very comprehensive idea of all these disciplines. Okay? Then you can actually go into the RF design. And then its interdependence is very important. And just I mentioned that how this interdependence are going into this. There is a famous optical linear design. That noise, linearity, gain, supply voltage, swing, speed, so on. They're all interrelated. They're interrelated, and an RF design involves all kind of faculties or disciplines in the regions. Okay? Now come to the next. This is the summary sheet. Whatever I have told you. So these are summarized into 8 questions. So if you are able to answer this, that means you have understood my case. Look at the first one. Phase shift of the signal is significant over the extent of components because its size is comparable with the voltage. Have you understood this point? So that's fine. Go to the second point. The reactance of the circuit must be accounted for, particularly those associated with the parasitic of the active device. Transistors, CGS, CDG. Clear? You have understood that point? Third one. The circuit losses causes degradation of quality factor, reduction of frequency selectivity, and noise performance. You know that quality factor? So if the quality factor is lower, then you have a broad. For a narrow band, you need high quality. Quartz crystal, 25 4. In this case, quality factor for a silicon, 3 or 4. So there is a problem. Fourth point, noise especially arising from the circuit can be significant and its effect needs to be modeled. It's a very well studied materials that noise of each components, active and the passive, has to be modeled nicely and completely. Otherwise the circuit performance will be clear. So noise performance. Fifth, the electromagnetic radiation, capacitive coupling and substrate coupling significantly alter the performance of the circuits. In a 1 millimeter into 1 millimeter, so many components are there, and that too the current is passing at a high frequency. So there will be mutual inductance. So there will be capacitive coupling of electromagnetic field through air, through the substrates. So all those will come. So that is called EMI-EMC issues. Those will come. Even some of the components might act as a radiator. High frequency, small components will act as an antenna. So those things will come into this, the coupling part. Reflection issues. Yes, I told you that when it is, the impedance is not matched with the load, the signal will reflect back to the source. What will happen? If it goes back to the source will be heated up and source will be damaged in that. Which is defined by what? The S11 parameters. If S11 is poor, then your reflection will be huge and that will cause degradation of your circuit. Circuit design should take care to ensure reflection do not cause any loss or gain or power amplifier or failure of the components. So that point will be clear. If not clear, then you can, because all this point should be clear during this first half of the lecture. The eighth point. The nonlinearity which causes distortions and unwanted frequencies, you are clear, is undesirable. That's why your percent points and your input signal is small. But in some cases you require the nonlinearity. Multiplications of two signals. Mixer is a nonlinear operation. Or an oscillator. This is a nonlinear. So you need sometime the nonlinearity of the circuits. Okay? But that is also in a very constrained way, so that it never goes to unstable state. Okay. The mixer, the local oscillator and the RF input signal, the frequency and amplitude are adjusted in such a way that to give more stable output systems. So nonlinearity phenomena can also be used in case of these RF circuits. So clear? 1, 2, 3, 4, 5, 6, 7, 8 points. So this part 1 is over. If you have any questions, you can ask me, fundamental questions. So I am going to the next one. This is noise. I will give a very simple approach in explaining the noise. And then I will go to model, how to model the noise for my noise systems. The first and foremost noise, all of you know, is thermal noise, 4 kTR. And the noise, how to model? You can use this as a current source or a voltage source. In a voltage source, there will be resistance will be in series, and in a current source, there will be current source because of the noise in parallel to the resistance. So there are two approach. One is the voltage source, and that is the current. What is Vn bar? It is the average voltage. Remember that it is Vn bar squares. So it is the mean square voltage, which is equal to 4 kTR delta F. Delta F is the bandwidth. When you not consider delta F, then it is the noise spectral density per unit spectrum. Delta F equal to 1. But actually in the definition, it is 4 kTR delta S. Now the same thing Vn bar square, when it is in series with the resistance, are reflecting to a current source In square equal to 4 kT, then R is divided by 1 the G, so that is the conductance. So 4 kT G delta F. That is, you know, for pure resistance. But look at the transistors. how this can be explained or modeled in case of a transistor.